This is a talk that's different from the others in that it basically has almost no technical content, except an example, and there is mostly invented, so that you actually know what's going on. And the idea is that I would like to present you a conceptual model of what we're really doing when we're doing math. And arguably formalized math, if you understand formalized as taking the computer to help in all of this, that's what we should be thinking of. It's kind of like a sociological study of what we're doing when we're doing math, and I'm disregarding the fact that mathematicians and computer scientists, when they're doing math, drink coffee from time to time and breathe and do all kinds of things like that, but really trying to get at the central aspects of doing math and kind of the knowledge that's involved and so on. And this is the condensation of almost 2 decades of discussions between initially McMaster and Bremen at the time, and now McMaster and Erlangen and Ljubljana mostly. That's really what we're, Jacques and Florian and Katja have been involved in this and helped evolve that. So we want to have a holistic model of doing math. And the picture I want to imprint on your mind is that of a tetrapod. And a tetrapod is these guys here. Tetra means 4. Pod means leg, so a 4-legged structure that also has, and that's important, kind of an outer tetrahedron. And so that's the shape I want to remind you of, and there will be lots of these diagrams in my talk at various points in time to remind you of this. And what's behind that is that we have identified 5 aspects of math. 4 of them are going to go into the corners, and you have heard of them. Deduction, for instance, that's activities like exploring theories, formulating conjectures, constructing proofs, verifying proof, all of those things. Not necessarily formally, but also informally and on blackboards and all of those kind of things. But the deduction aspect is really about proving things and setting up conjectures and so on.
Looks more like a theorem 1-1. It looks more like a theorem 1-1 instead of definition 1-1.
Oh yes, well, observation 1-1.
Okay.
I'm trying to define, well, I'm actually trying to define these 5 words here, and I define them by example. Deduction as the thing we all know and love. And if you think about it, those are the things we're doing here. Then we posit that there's another activity that's important and going on, and many of you have actually been dealing with this in Lean as metaprogramming, in Cork as kind of built-in programming, natural number literals in automated theorem provers, you name it. So computation, which is really taking mathematical objects, simplifying them, recontextualizing conjectures in a different setting, running a program while you're doing something else. You know what I mean. We've tried to have all the words end in shun, which means sometimes they might be slightly weird, and the third one is really weird. It's concretization. We would have used the word data, but it doesn't end with "schon." So it's kind of derived from a verb that kind of does the action. And so we're thinking in concretization as making examples, making concrete examples, making the LMFDB, the L functions and modular forms database. I always get it wrong, but I did get the acronyms right for once. They have terabytes of numbers about number theory. Right? Very simple things that you can store in a database, and more of them. The groups people have lists of generators of the first, the groups of, all the simple groups of order up to 1023, if I remember correctly, right? Huge lists of very simple things. That's what concretization is about. And that's something we do. We make examples, we make simple examples. Right? The complex examples, we always hear this pun about category theory as being the theory where the examples have examples. Complex examples are really mostly theorems in disguise, so they should probably go into deduction. But concrete things you can put into simple data structures and run tests over and manipulate with Python. Those are the things we're thinking of when we do concretization. And finally, narration. Yes?
So do you mean, for example, in the LMFDB example for concretization, the actual data type might simply be an integer, which is very simple, but it might be a very deep statement that something is 2, right?
That is true.
See that as concretization? Because it can be a very hard theorem to prove.
No, those I think of as deduction.
Okay.
Because there the data type is true-false. Right? And these things are not going to be without overlap. But we think of them as different activities. And so having concrete examples, which is why we didn't call this aspect examples or counterexamples, because this notion of the objects being simple enough is missing. Yes?
Is being concrete a matter of degree, or is it absolute?
Absolutely, all of those are. All of those are going to be a matter of degree, and all of them are kind of by simulation equivalent. Right? Any computation you can do by running a theorem prover. Any theorem prover is implemented in a programming language, right? So they're in a way mostly equivalent, but which is why I'm saying it's not technical but conceptual. It's kind of doing computation is really different than doing deduction.
So you're really labeling different activities.
Yes, and the products of these activities and the objects of these activities. I'm going to go even more in this. I hope at the end of the talk you'll have a feeling of what I was trying to say. And I'm kind of being, I'll circle the model and kind of hopefully come nearer to it. And, oh yes, I didn't say it, but if I don't get at least one question per minute, I will consider myself to have failed with this talk. Okay, so you're doing pretty well still. Okay? The last aspect I want to, last of the corner aspects, which is completely different, I think, to the others, like they're in a way primitive activities, is narration. Right? When we have a theorem, we write it up. We write a story around it where we say, oh yes, and wouldn't it be nice if we had this, then we could have those applications, and by the way, old Tarski had the conjecture that this might be true, and nobody could prove it, and so blah-de-blah-de-blah-de-blah, we tell a story aimed at human beings. Right? We do it in LaTeX. where concretization we do in databases or JSON files. Computation we do in C, or if we're more enlightened in Haskell, or Lisp, or those kind of things. Deduction we might do in a proof assistant, or weird logic we've just
Michael,
had.
since you asked, I'll keep interrupting.
Good.
So, how is this meant to change my life?
You're supposed to, just for one thing, be able to say that PVS is probably somewhere here, as opposed to, I don't know, Isabel, which might be more on that line, and so on. It gives us, we believe it gives us a way of shaping the space of all systems that we kind of see and compare ourselves to. This is going to be, or I mostly use it as a map of people and systems and ideas, and I can place them. And it's also kind of like a roadmap of where we want to go. Kind of most of the systems are born here and kind of branch out a little bit because they must. And
algebra systems are born there.
Yeah, computer algebra systems are born here. Proof systems are born here. LaTeX is born here. OEIS and LMFDB are born up there. But kind of one of the things where LMFDB is getting very good at is kind of going down that line with all the nulls and all of these things, because just numbers doesn't cut it either. Okay, and describing that, getting a conceptual model of that, that's what I think this model might do.
You can easily use this model to predict where a lot of the system will be developing their features next, and you can see it. Lean, with blueprints and many of the other things that are doing, are rapidly moving towards more features for narration and organization. And they're explicitly, in MATLAB, trying to avoid computation as much as possible, no matter how much James is trying to push. And one of these days, we might even discover that examples are cool things. And I guess some people were doing...
Katja has been working on this with Jure.
So you
Yeah.
And besides, are part of area of input blueprint to really make sure that you've proved what you wanted to prove.
Yes. So, but this is kind of the boring stuff. The interesting thing, and which is why we call the model the Tetrapod model, is that all of these corner aspects, the four aspects, they share certain things, and typically you need them to, if you want to combine them, you need to hinge them. If you want to combine systems, you need this funny thing I haven't talked about yet, organization. So that which way do I have to go? Yes, which is kind of the hinge in the middle that allows you to maybe go from one to the other. And so in the simplest form, this might be names that we call a certain function in an implemented function in a computer algebra system, factorize. And the same thing, namely the thing that is tried to, that we try to achieve with the factorization function, with a relation called prime factors of, or something like that, in a deduction system. And if you do your narration in French, then I'm sure it has still another name, right? And you might want to have it at the center, because it looks like in most cases names and possibly types and possibly certain axiomatizations and so on might actually play a role there. to shape what is in the middle. What are the objects? Peter.
Just for illustration, how would other sciences look like when you want to have a pod model or so, physics, chemistry, language studies or so?
We have looked at this a little bit. Let me give you a preview. There it is. We've tried to do it for CS, which is not really a long ways away, but we're trying to do it, and I'll come back to it. My suspicion is that this is pretty universal, but in math, kind of the structures are more overt than, say, in when you're trying to learn to play the tuba, as Dana Scott always said, right? There much is buried, and you have to kind of coax it out, and in math we have the great opportunity that when a mathematician does a definition, he writes definition something or the other, and then makes the definiendum boldface.
Part of the idea of creating this, well, part of it is for system designers, much more than for mathematicians. This is stuff that mathematicians just do. And it is our bemoaning of the fact that most of the systems that exist are sort of corner-centric and should be much more aware of everything that is done and, you know, trying to take care of it. And as Michael said at the very beginning, in some sense, this is sort of technical content. So for a lot of people, this is too boring and they don't work on it. And then the tools remain bad. So some people have to devote themselves and be engineers and make good systems to reflect the practice.
So we're doing essentially the philosophy of doing math, right? This is what philosophers always do. They kind of try to categorize what we're doing and what does it mean. And we're dabbling in that a little bit. More questions? Then I'll probably try to give you examples, and that's probably more helpful than any of the general blah blah that we've had so far. Think about the Fibonacci numbers. In the organization, we might have a theory. Come on, you're supposed to. Well, we're supposed to have. We have a theory. Doesn't work anymore. A theory of Fibonacci numbers that gives us a name or even two names, fib, and for the function, and maybe a bit of a specification of what the Fibonacci numbers do. Okay? And it might be based on other things, and we want to kind of keep things modular, but that may just be a quirk or an accident of Erlangen talking to McMaster. But really also I think what this gives to us theory graph people is that it kind of gives us a place where things like modularity or so actually belong. So that would be the organization thing. Concretization is really easy, right? We have a list of numbers. They get longer and longer. Like that's concrete data, a list of numbers, very easy. You can stick it into the database, not a problem. Narration. We tell stories, right? Fibonacci numbers are named after the Italian mathematician, blah, 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 and so on. That's what's in Wikipedia. And it's kind of a different thing than that. Right? Different kind of information, different target group, and so on. Computation, right? There's a Python function that computes them. And finally, deduction, we give theorems and proofs about Fibonacci numbers, and we might be interested in something like this, and prove it, and dump it in MathLib, or the AFP, or whatever. Okay? So each of these things kind of has a special place where it's supposed to go. And what you can see is we're still talking about the same things. Most of what we can do in the corners really has something to do with what we stuck in organization, where we've been going back and forth of what exactly has to go into organization. And since this has no technical content, you're free to have your own intuitions. And I think we can probably make a huge sociological experiment, but I think we're also good if we don't. Okay. Right. So, again, there are all these corner systems. There are even some purebred organization center systems. And the hope is that this kind of landscape gives us a way of hooking them up together. Or having systems that kind of can do not only a corner, but maybe a whole edge of the tetrahedron. Or maybe even a whole plane of the tetrahedron. There are 4 of them, so there's lots of space to actually make your system great there. Or even to have something that fills the whole tetrahedron. And we don't see many systems that even attempt that. And if I can actually take my tetrahedron and throw it at somebody, then that might be a reminder that there's more space to explore around the system. And your systems tend to get different when you explore bigger dimensionalities, and possibly better. And as kind of an academic community, I would like to challenge us that the only system that's remotely three-dimensional is Mathematica, probably. I find that embarrassing.
Much to my chagrin.
Yes. So we have to acknowledge that at some point, but they're doing, and probably driven by the market. We suspect that if you have the power to just tell people, 100 engineers to say, well, let's conquer another corner, which has happened at Mathematica, and then you get systems like that.
So I know they bought Waldmeister at some point, but that would be like the end of their deduction, or not?
Yeah, we have systems that kind of cautiously go along one edge a little bit. And we all know Makarios Wenzel's journey, basically out of the deduction corner into more of the narration corner, starting with Izar, which is kind of more narrative, having all these caches or whatever he calls them, where you can embed later in Isabel, and in that later embed prologue, and everything kind of works in the right context. Those are things where we're making great progress, and it changes the systems. I mean, I've seen with Burkhard, something or the other from Paris, he gives his talks in slides developed in LaTeX in Isabel. Amazing. That's kind of what we're hoping for. And he did that before he even knew the tetrapod. So here's a little tetrapod for CS. We're thinking of a string matching function. That's not it's probably more of a CS object than a math object, even though mathematician says we can do string matching. Right? So in the middle of the organization, we might have kind of a specification of what it's supposed to do. That basically tells us what's the object we're talking about. What's its type? Maybe a couple of axioms and so on that go in the middle that describe what this thing does. If you don't have this, if you don't adhere to the specification, you shouldn't call yourself a string matching function. Here, of course, that's doesn't work. Right here, up there, we kind of have things you probably have seen in CS as well. Think of them unit tests. If you're not doing that as a function, then something is wrong. We don't really use examples as unit tests in math that much, but right? Benchmark suites, and all of those kind of things are more CSE concretization examples. Of course, we have deduction, theorems about string matching, maybe verification, all of those things. Computation, there's a program. Narration, where you write funny LaTeX about these things.
Two questions. Actually.
Yeah.
One is you seem to interpret organization as some kind of specification or some formal representation. Is that what you mean?
No, it could also be in English. The difference between specification in English and in a formal system. Actually, this formal system is invented. We just made it up for a paper. So you can ask yourself, is this a formal system at all? But it's more what we're trying to do. We're trying to pin down what the object is, rather than what are the infinitude of properties it might have. And some of the properties are, in a way, defining or characteristic or something like that. That's what we're really trying to capture here.
But there's probably also room for, this is where ontology is going to go.
Yeah.
Stuff like that.
Or even open math content dictionaries, which have specifications like plus is the plus we all know and love. Right? It doesn't have to be formal. As long as it kind of identifies the objects enough that we can work with them.
And is something like literate programming an illustration of the tetrapod, or is it just something that belongs in some nook of the tetrapod?
Yeah, literate programming, I think, is somewhere here. Right? It's kind of on this internal face, right, between organization, narration, and computation, I would guess.
So classical literate programming is like on the edge between narration and computation. Like a la Knuth.
Yeah, that is true. But a la Jupyter, it would be somewhere more in the organization direction, I would
The
say.
whole point of it is by doing it, you actually force yourself implicitly to think about it harder so that some of the specification kind of gets dragged in despite your best wishes as a programmer if you want to tell the story properly.
Yeah. Okay, more questions? We had a couple of examples. So there are systems that cover these, and and of course the space is much bigger, but some paradigmatic examples. So for organization, we have these, we have the languages, we have the ontology languages, we have description logics like ALC. For concretization, we use SQL or JSON. For computation, we use programming languages like C or, as I said, Haskell. Logics, just taking one higher order logic. And for narration, we have document languages like HTML or LaTeX, or if you're as old as me, you may have seen ROF or those kind of things. And then we have the systems, the things that work with these languages. We have reasoners, Sparkle, Sparkle reasoners, query languages for the organization, triple stores at the organization level, but maybe also if we want to go more formal specification languages and things that work with these. We have databases in the concretization level. We have interpreters, compilers in the computation world, theorem provers.
And what does the KPG stands for?
I forgot, I was hoping you wouldn't ask me.
Sorry.
Knowledge processing.
Florian?
As Google Lens.
Document, knowledge,
Knowledge processing.
processing tools.
Oh yeah, whatever the intention was, that's a good interpretation.
Yeah.
Right, that's what we're talking about. This is the landscape. And we're really happy, even though we have 5 aspects. We don't really span up a 5-dimensional space, which would be almost trivial and worth nothing, but has something that really captures quite a lot of stuff, and I would like to explore that. But before, let me tell you, it's not quite true that Mathematica is the only contender for something that has all 5 aspects. The OEIS, of all things, right? It was born in the 1990s and is virtually unchanged since. But
It has been 60 years recently. Oh yeah.
I know, but the virtual version of it is that's a bit younger. The interface is still in the 90s, I would say. But
They changed it to a wiki in 2010 or 11, so they changed the interface, you could say. We had Neil Sloan's talk at MathWiki in 2011 about how he
that's not what is on oeis.org at the moment.
He really claimed that he changed it to some version of, I don't know, MediaWiki or whatever.
Okay, that's not what I'm seeing. That's also not what we're seeing in the back end.
Okay.
He hides it very well.
Fools me. But the content is interesting, right? You have all seen, like, we have these sequences, and we have 360,000 of those. Fibonacci numbers is one of them. The interesting thing is really the data model, and even though it kind of creeps me out, this is what's actually in the database. Lines that are prefixed with %f, that means we have a formula. And then %f this, which means there's a formula for A00045. And then you have ASCII arts. Sometimes with narrative text around it, without dollars, that distinguishes one from the others. It's really annoying when you want to parse this because they will just use interpunctuation, comma, where, or something like this, and you don't know where the formula begins or ends. But that's really what is there. But the nice thing is, we have all the things in here, right? We have concretization, %s. We have organization. Everything has a unique identifier. Very simple organization, right? We have probably a little bit of specification right here. We have probably something I would consider narrative. It's here who has talked about these things. We have this is the this is formulae about it. We have other theorems about it. This is certainly narration, and so on and so forth. And we have metadata, which might be organization as well.
What would you call deduction then? These formulas?
Probably. Well, this is the generating function, which really is what is a Taylor expansion whose coefficients are just the Fibonacci numbers. That is really a theorem that would need to be proven.
Doesn't have any proofs.
Yeah.
It doesn't have any proofs, yes. Well, it has references to papers that give us proofs.
Yeah, that's knowledge management. That's not. There's no deduction in this.
So there's no reference to the next.
Yeah.
There's a reference.
Yeah, yes.
Okay, only 2 dimensions. Yeah. But it's from the 60s, come on.
Spires.
Yes, yes. But, right? To me it was quite interesting. It even has, we're not seeing this, but some of these have Python codes that generates these sequences, and Mathematica 2.3 code that generates something else. And there's quite a wealth of interesting things.
Lots of Maple code.
Hmm?
Lots of Maple code.
Oh, yeah.
Because Bruno Salvi's G-fund's been used to guess a huge number of these recurring tests and stuff.
So this is vaguely, let me say, it's vaguely tetrapodal. And if you really want to do something with it, we've tried to semantify these kind of things so that they become more machine accessible. Then you have to think about the tetrapod. Right? So what organization does, really, is it gives us a uniform vocabulary, and we use that, and that interacts with the other forms, that for narration, where we often have references that are extremely ambiguous. Think about the word simple, or degenerated, or canonical, we've heard in this workshop, and so on. They have lots of meanings, and by referencing into the organizational aspect, you can disambiguate them. Very often, organization kind of give you legends to the schemata in the concretization aspect. You can think of the organization as we've used that in the Open Dreamkit project, as a kind of a interoperability guide between computational systems. In deduction, you could use it to collect all the theorems about a concept. And in a way, you can get by with a very weak notion of organization if you want, because you can always travel down the legs into one of these other aspects to get more semantics. You can travel down the deduction leg to get lots of properties given in theorems. You might, I'm sure you can elaborate further yourself. Narration really, for instance, occurs as documentation. I don't think I've ever seen, no, I did. JSON has no native comments, but that's the only system I know that doesn't have comments, which we use for documentation by writing natural language into them. Everything else has them. Right? We need it looks like. Yeah, legends again. Glossaries, all of those kind of things we use all the time happen in narration. After all, we're humans, and narration is our natural form of communication. Not C, not Haskell, not even Lean, many people think. Right? The natural form of communication is English and blackboards and all of those kind of things. Narration.
Or French or German. Or other language.
Or ChatGPT.
Yeah, okay, I may. Right? But there's a reason. We're not just sequentially showing mathlib in audiences like this. Computation, wonderful, it computes values and those kind of things. Concretization, we have examples and counterexamples for deduction, unit tests and benchmarks and so on for computation, data for machine learning models, all of those kind of things come from concretization, that's important. Deduction, of course, has the power to justify stuff. We can justify shortcuts in computation where we can prove that there are these things like in the four-color theorem, right? there's infinitely many cases you don't have to even look at. Those kind of things. Completeness of concretization. If you want to make sure that the atlas of finite groups up to the order of blah has all of them, you have to convince yourself somehow. And you're in deduction automatically. Right, so that we really want at the synergies. And we want to have multi or cross-aspect tools, I believe. And I challenge you to seize your evil practices and come out of your corner. Right. If you're not asking questions, I'll have slides.
I could repeat my evil remark from DAX 2 that on the previous slide. I'm still missing where the learning abstraction induction is, because it doesn't seem to fit in your concept of deduction. It doesn't so much fit into computation and concretization. Like, it seems to be some sort of thinking activity that is not exactly deduction unless you really twist it like you could.
Right. We have been thinking about renaming deduction into duction. So that it actually covers induction and abduction and any other ductions. And we've kind of never gotten around to it. And it would be even more weird. But no, the induction is in the deductive remit, I would say. You cannot imagine how many days and weeks we've spent on trying to get good words. And we know we've failed.
This naming it deduction would be innovative. I would.
Less is more, yes. If we get Katja in the room, then the four of us might even have a majority for renaming, yes.
You could copy this Elon Musk and rename it to X-duction.
Yeah, I'm not sure I want. Shankar, yes.
You seem to intuitively have some kind of metric.
Oh, yes.
On this, but
It's take the distance, which is the square root of x squared plus z.
Yeah, I can see you putting things in various places, but I don't know what metric actually is.
Yeah, I wouldn't know how to measure it automatically. But it's like with porn, right? I know it when I see it.
It is maybe like porn, but it's, it's something that still have to be usefully measured. And
oh, I would love that. I would absolutely love that.
It is subjective, and in some sense, I think I'm not the only, Michael's not the only one that go ahead, prove us wrong, come up with better words. Keep the tetrahedron, please. But otherwise, come up with an even better version of this.
Yes.
To guide system builders into covering the right features. This is a piece of propaganda. Hopefully you don't mind me calling it that.
No. I subscribe to that.
Trying to push forward system builders to think about this.
We haven't really thought about numeric metrics, but I suppose one could just look at the system library and try to estimate how many lines or characters are proofs, how many are algorithms, how many are text, and how many are concrete values. That would probably be a pretty good approximation.
And gzip them first, of course, or something.
Yeah, we would place the system in the...
Yeah. But yes, I think measuring would be an excellent thing to do.
Also, most of the time you can kind of tell very easily. Like the systems will self-advertise using words like prover or the algebra system. you can tell from the people and the conferences that are in. It's usually pretty clear cut.
Well, I guess the interesting question is when you say, oh, you're somewhere between this and there, like, how far, 20%? Like, can we measure this?
I would be perfectly happy with just a, what is it called, a pre-measure, like an ordering of systems, right? Where you can basically say, well, at least we know that PBS is nearer to its corner than Isabel. Who knows, right? Those kind of things.
A map where systems and other stuff is really situated in this.
We've thought about this, we've failed in many ways. One of the things we were thinking about was using 3D printing to do a little bit of that, but we couldn't quite find the right materials that were see-through enough. I don't know, a synthetic digital map in a hollow cave might actually help, but...
It's really hard to... It's all going to be fuzzy bubbles.
Yeah.
You know, for example, yeah, fine. LaTeX gives you the best typesetting that we currently know about.
But it's just computation, it's during
It's just computation. If you use Mathematica, you typesetting, it's okay. Allows you to like do a lot of stuff. Its typesetting is definitely much, much below the quality of LaTeX.
Almost all systems have one aspect that is like the primary aspect. And if they do other aspects too, they're usually not competitive at the other aspect.
Right.
Like it's very no systems that can be competitive at two aspects.
Right. Yeah, I agree. We've done it.
Well, yeah, I want to remark on that though. Like this picture, I mean, sort of bakes that in. It says like, oh yeah, like we live on this, you know, world where like, oh, if you are on the narration corner, then you are not in the deduction corner. You cannot be both, right? And that's not necessary. I don't think that quite like you can be good at two things. You can also be bad at two things, and that is a direction that is not represented in this picture, right?
That is true.
Fundamentally, what we want is something that is good at all five things.
Yeah.
That's what we want.
Sure, sure. So then why not like maybe we do need a cubical model.
You were bashing declarative verbose proofs yesterday, so what is this?
Yeah, maybe we should stop doing simplex and do the cubical model.
Go ahead.
In terms of getting good at all five aspects, it seems to be that no one will ever build a system that is actually really good at all five at the same time. So we might forever face a situation where we have loosely coupled systems that optimize for different aspects. And we have to think about how can we combine them in the best way.
Yeah. Well, actually, I would claim that this might not be correct because I think I have a counterexample. Andrea and I have produced 3 systems that are pretty good at all 5 of these. They're 28, 30, and 32 right now. Right? So we humans are pretty good at this, which is really the inspiring thing.
Well, maybe we should just stop then.
Oh, I have such a nice characterization that I would like to show you essentially, which is if you think not only about the corners, but about the edges and the faces and so on. And kind of look at the opposing thing, right? If you look at kind of an aspect pairs, deduction and computation are things that have a very rich meta-theory. We know a lot about them, and we know much less about concretization and narration. Even the linguists don't really know in that depth. Narration and concretization have in some way simple languages, if you think of English to be simple. Deduction and narrations, we have theorems and proof in both of them. We don't really have theorems and proofs in the other two. We have computation, and concretization is really driven by things like normalization. You kind of normalize out of computation to get concrete objects, typically. We have deduction and concretization. We have kind of decidable well-definedness. If you think about it, and computation and narration are Turing complete. Which deduction typically and concretization typically aren't. So we have interesting kind of effects that are, as who said it, that are kind of baked into this image, if you think about it, which really tells me, or makes me believe, that this might be helpful. Right? Also, the aspects have their own advantages and disadvantages, right? We have formal proofs that have the advantage of being correct, but if you think about the other three, kind of the opposing face, then you have them, those are much easier to use. And the application of formal proofs is verification of X. Yes.
So I was already saying this at some point. I was at this Barendrax retirement party a long ago, and he was really proud of this achievement where in proof assistance you have the computing part, which is decidable, and then the reasoning, so deduction part, which is the undecidable part. So he would probably very much object to your last two lines there. Like he would tell you that you got them swapped probably.
Yeah, I have a long and joyful history of being being accused by Henk of getting it wrong. So yeah, and it's more of getting you to think about this, right? This may be the most technical thing we have here. So it's surprising, and I think I want to close with that, how much kind of the spatial model gives you about the understanding that we kind of implicitly have as a community. As a community that formalizes aspects of math. The mathematicians kind of know these things too, but you could kind of threaten them for their life and they couldn't even formulate them typically. Or only certain bits and pieces. But I think for us it's important. And that's really all I wanted to say. And if you have further questions, criticism, and so on, you can also talk to Jacques or to, who is really our, let me see whether I can find, so it's really, if you think about people here, we're involved in the, Jacques is near this corner, even though he does everything else.
That's where I was born.
You were born, yes.
I reversed everything else along my journey.
Right. I would say I started in deduction and drifted towards organization and back and forth and so on, and kind of overshot into narration quite a lot. Florian is really in organization, I would think. Katja is born in concretization and starts even looking together with you and Andre into deduction. And so,
And Bill was born in deduction.
Born in deduction and invented many of the good ideas about organization and but really is a deductionist. Or as we say now, ductionist. Yes, Shankar.
What does it mean to be bad at organization?
I don't really like to say good or bad at things. I don't think that's a very helpful thing. Whether you're attempting to do something. I think you can have most systems have a relatively simple organization systems. If you think about Wikidata, then really the only thing they're giving us is the URI, which is standardized because you can look it up. And it has narration on it. But there's no real clear correspondence between bits and pieces. Sometimes it says definition as a section heading, and then come 3 mutually inconsistent definitions and for different things. And some people do this and some people do that and so on. So they're into storytelling. And they have concrete examples, but there is no, but the organization system is there extremely simple. They don't have types, they don't have all kinds of specifications. And sometimes they have relatively unspecified links. And in Wikidata, they're trying to do better. And it doesn't scale very well at the moment, in my opinion.
I can give an example. A lot of simple proof systems fall into this category of not handling organization, and then organization will basically be something that's built on top. So like an example that comes to my mind is like MetaMath, the system that is, so there exists an organizational sort of layer that is built on top, but the system itself knows like definition, theorem, and that's it. Just like you write, we don't even have imports, right? Like who needs imports? It's just keep going, right? That's, it's really a pure proof system. It's just proof data, nothing else. If you actually want to work with that at scale, you have to build some kind of organizational mechanism, but then that becomes like a secondary layer on top of the thing. And then you can say about the broader system that it's attempting to address organizational aspects, but if you look at just the pure sort of this lower level thing, then it's literally not a part.
Yeah, but at least there you can see the knowledge. You know where it comes from. In a system like Mathematica, all of its knowledge is buried in pure code that you have no access to. So, the documentation promises something.
Well, I would say that like addressing organizations, like having section headers, right? Like that's a concept that like you don't have to build into your programming language or whatever. Like, should modules exist as a concept within your language? That's like you're addressing organization when you add such a feature, right?
If those section headers are arguably, I would say, narration.
Oh, but yeah, and
well, they're organizational aspect of narration.
Yeah. It is now,
Time for cake.
yes, time for cake, I think. And I hope this discussion goes on for weeks.